Okay, today we're going to talk about angles and standard position, but for all four quadrants. Last time we only talked about standard position, and those angles always ended up in quadrant one. Today we got to deal with all of the other quadrants as well. So imagine that you've got some point C. It's on the terminal arm of an angle theta, and that is in standard position quadrant one. So let's just give ourselves a point first. Point C, we'll call it coordinates x comma y. Okay, so there's our point, and we could draw that terminal arm in. There you go. Just remember, it always goes counterclockwise from that x-axis, and this would give us our angle theta. Now, if you were to reflect this across the y-axis, you're going to see another angle created. That's another point. Now we could call that C prime. Basically, it's just the original point C reflected over our y-axis. Okay, that's going to create another angle in between the x-axis and that terminal arm. Now that has the same measurement as our original theta. It's the exact same terminal arm, just flipped, mirrored. Now imagine you did that a second time, but this time over the x-axis. Okay, so we're going to go down into quadrant 3. Now, I think you can imagine what's going to happen. I've got another point xy. This is C double prime this time, but I've actually got to fix my coordinates here. X and y in quadrant 1 are both going to be positive, but in this quadrant where we flipped it, x should actually be have a negative coordinates. Let's fix that. That should actually be negative x. Positive y still, because we're above that x-axis. Now down here, quadrant 3, both x and y should be negative. Okay, so those should actually both be negatives. Now if we do this one more time, flip that terminal arm into that other quadrant over the y-axis one more time, I get another terminal arm, same point just being reflected. This is the third time we're doing it, so C triple prime, positive x, negative y. Now for the two that we created underneath that x-axis, the angle from the x-axis to that terminal arm has the exact same value as the other two. All four of these angles represent theta, the exact standard position angle we started with. The issue, now it's just reflected, and it could be in one of four places. The only thing that changes is the sign of the point on that terminal arm. Okay, now we're going to use this idea to find the trig ratios for any point, no matter where they are, in relation to that first quadrant angle. That's the goal here. Okay, so if you keep that idea in mind, you've got a chart down below, which we can fill in a couple pieces of information. So quadrant 1 first. Here's my terminal arm represented by R. My point is xy. I've got an x dimension, a y dimension as well. So for sine of theta, that formula was the y coordinate of that point divided by the length of that terminal arm, so R. Both of those are positive, which means in quadrant 1, my sine ratio is also going to be positive, since we're going to divide a positive number by another positive number. If we do this for cosine, its formula was x over R. And again, both of those are positive, so cosine is going to be positive here also. If we do it for tangent, the ratio for tangent was y divided by x. Again, all positives. All three ratios in quadrant 1 end up being positive. Okay, this is going to be helpful going forward. Now, if we do the same thing for all of the other quadrants, what you're going to notice, sine is going to become positive here, cosine negative, tangent negative. So I'll leave the in-between boxes for you to fill in to make sure you can get these signs of those ratios. You do have the answer key also posted for you. But you're going to notice that things are going to change as you move around this grid. Now in quadrant 3, you're going to notice that tangent is the only one that's positive. Okay, in quadrant 2, sine was the only positive one. In quadrant 4, then, the only positive one is going to be cosine. Okay, the other two are going to be negative. So in quadrant 1, all three are positive. Quadrant 2, only sine is positive. Quadrant 3, only tangent. Quadrant 4, only cosine. Okay, now that's going to be super helpful. Now that's a lot to remember with all of those formulas and signs and all that kind of stuff. So we have a little bit of an acronym to help us out here. So if we need to figure out really quickly which ones are positive and where, both of these could help depending on how you want to think about it. The first one is called the Casp Rule. And I'm just going to write some things into these quadrants. So sine, all, tangent, and cosine. Okay, now the way this works, if you remember how to number off quadrants, this is Quadrant 1, this is Quadrant 2, Quadrant 3, and Quadrant 4. Now if you follow this around, if you start at Quadrant 1, if you look at the first letter, maybe I'll highlight them in a different color here. So A, S, T, and C. So as long as you go in numerical order 1 through 4, the first letter you can create an acronym for. So A would be add sugar to coffee. And you can make any one that you want, any way that helps you remember it. So add sugar to coffee is one of them to remember which direction to travel around that Cartesian plane. The other one is the Casp Rule. So you're going to start in Quadrant 4 this time and still travel counterclockwise. So C-A-S-T for Casp. Now, whichever one you want to use to remember, by all means. Okay, underneath, it's an important piece to note here, which we kind of talked about. So it says the ratios are the same in each quadrant using the reflected triangles, although the only thing that changes is the signs. So you're given a reference angle of 35 degrees. That's in Quadrant 1. Now, if you flip it over that y-axis, like we did before to get C prime, you still have the exact same reference angle of 35. Things are just in the opposite position now. Okay, you could do that again, flip it over the x-axis, it creates your angle of 35 underneath in Quadrant 3, do it one more time, and you get your angle of 35. Now the other angles that you see in there are actually those angles in standard position. Remember we said they start from the x-axis, go that counterclockwise direction, and they travel around the plane. So now we're going to have two different angles that we need to worry about. Okay, so we can reflect terminal arms into each quadrant to form 4 different angles in standard position. So if you notice, I had originally 35. Second one we had was an angle of 145. Then it changed to 215 and finally 325. So 4 different angles to represent the exact same reference angle. Okay, we're going to get into that in a little bit. Okay, so those 4 different angles circled in purple would represent the standard position. We would call them principal angles as well. Okay, if we draw an acute angle with the x-axis and all 4 principal angles, that's going to give us that 35 degrees. Okay, that angle is the one that is on the terminal arm and meets the x-axis in every single time. Terminal arm, x-axis, terminal arm, x-axis, terminal arm, x-axis, and all of those are 35. Okay, our reference angle then is that positive acute angle formed with the terminal arm and that x-axis. If you've forgotten what the word acute means, it just means that it's going to be less than 90 degrees. Okay, so it will always be less than 90, never bigger than. Okay, our angle in standard position, or our principal angle, can be bigger than 90, but the reference angle of 35 in this case, always less than 90. Okay, so we flip it. We'll talk about just some angles and how to find those reference angles. So the first one, we're asked to draw an angle of standard position and find its reference angle. So 75 degrees, if you were to throw some labels on here, they would be 0 degrees, so we're going to always start from here and travel counterclockwise around. Okay, so top's going to be 90, this will be 180, on the bottom 270. Okay, they're always going to shift by 90 degrees, right angles. Now 75 degrees is in between 0 and 90. So if you draw a terminal arm, and again, it doesn't have to be exact, it just has to give you enough information to get close to where you need it to. Okay, so that angle in standard position then, start at the x-axis, travel counterclockwise to your terminal arm, which we have now done. Now this angle, 75 degrees. Okay, that's our standard position angle. Okay, the reference angle is the acute angle formed between the x-axis and the terminal arm. Sometimes those 2 angles are going to be the same. So you can say for this one that your standard, I'm not going to have enough space to do that there. Standard position is going to be 75 degrees. Reference angle also 75 degrees. Okay, sometimes they're the same. For B, we've got an angle of 282 degrees. Now that's going to be in between 270 and 0. Okay, if you were to keep going all the way around a full revolution, this would actually say 360 degrees, and that would be 270. Okay, a full revolution around is going to make it right back to 360. So we're in the fourth quadrant here for this one. 282 is what we're drawing, so somewhere closer to 270. And again, it doesn't have to be perfect. So there's our angle. Now let's draw this angle in first. If it's an angle of 282 degrees, we've got to start on the x-axis, travel counterclockwise all the way around to that terminal arm. Okay, so here's my angle in question. Now that angle is 282 degrees. That's our angle in standard position. Okay, we've started at the x-axis, traveled counterclockwise all the way to our terminal arm. The reference angle is the one that goes from the x-axis to the terminal arm, basically the other piece that isn't there. Okay, so our reference angle is the little piece in red that was missing. Now in order to find it, you could take 360, subtract out what you've already accounted for in blue, that'll leave you with the red piece. So if you subtract, you're going to get 78 degrees. Let's just double check my math. 282, take out that 360, we should have 78 degrees left. Perfect. Okay, so in red, that would be our reference angle. And in blue, our standard position. Okay, now remember that this terminal arm can always be reflected. So we can always move it, but that would change our standard position angle. It won't ever change our reference angle. Okay, so just keep that in mind. Okay, C says negative 118 degrees. Now, if we travel counterclockwise, that gave us a positive angle from our first lesson. So when we travel in the clockwise direction, that's going to give us a negative. So now I can travel the other way around this Cartesian plane. Let's throw some numbers back on there, 0, 90, 180, and 270. If we go negative instead, we need to be at negative 118. So I'm going to travel. Oh, I'm going to change these numbers. Sorry. Instead of going that way, we're going to go the other direction, clockwise, like I said. So instead of starting at 0, we're going to go downwards, and our first one will actually be negative 90. Okay, and then up here, negative 180. Which means the top one, negative 270, and this could also be written as negative 360. Okay, we're traveling in the opposite direction now. So we're going to draw in our angle of negative 118 somewhere in quadrant 3. Okay. Now the direction's important. So this direction, x-axis starting point clockwise to terminal arm, that will give us a negative 118 as our angle for standard position. Now our reference angle is underneath. So our reference angle is always going to be from x-axis to terminal arm. Okay, now that angle is 62 degrees. Okay, the one other piece we need is our standard position, because it always goes from our x-axis counterclockwise to that terminal arm. So it can't actually be the negative 118. We've got to do this a little differently. Okay, so x-axis all the way around to terminal arm, that's what we need to find. So halfway around that Cartesian plane is going to give us 180 degrees. If we add in the 62 degrees that we need to make it to that terminal arm, that will give us our standard position angle. So we'll take 180, add 62 degrees to it, 242 degrees would be our angle in standard position, because it's got to be positive. Okay, so that would take us all the way around. And last one, an angle of 150. So here's 90 on top, 180. And just for completeness sake, let's change those to the same color. Phone off here. Okay. So there's my 2, and 150 is going to be in between them. So somewhere in the middle, closer to 180. Now, That would be our standard position angle of 150, which would mean our reference angle, the one attached to that terminal arm and the x-axis, that needs to be 30 degrees, okay, to make up the full 180. Now, I know the other one is also attached to the x-axis and the terminal arm, but remember that that reference angle needs to be the acute angle. Okay, it can't be bigger than 90. All of the reference angles have to be less than 90. Okay, keep that in mind. Okay, you have the same little summary here like you did in the last lesson, which talked about cosine, sine, tangent, and the length of your terminal arm, which we wrote was r. Okay, when dealing with those trig ratios, you can use reference angles, terminal points, and the understanding of the ratio and quadrants for those signs to write exact values. So now we're going to get into things where my terminal arm might be in a quadrant where something is negative. Okay, so the point 2, -5 lies on the terminal arm of angle theta in standard position. Determine the primary trig ratios of theta. So we're going to draw a picture first. Okay, so here's a grid. And that's not very straight at all. Let's try again. Okay, so there's our grid. Let's plot our point. The point's 2, -5. So x is positive and y is negative. That's going to mean we're down in quadrant 4 somewhere. Don't exactly know where, but that's fine. Okay, so there's the point. There's my terminal arm. We need to determine the primary trig ratios of theta. So theta originally is on that angle in standard position. Okay, so remember that theta could also be here. We're essentially reflecting it enough times to get it down here. Okay, so they're the same. The signs are just going to be a little different, but the angle represented is the same. Okay, so let's go find out the length of our terminal arm first. So r equals the square root x squared. I believe it is plus y squared. Okay, so r equals the square root. 2 goes in for x. 2 squared is 4. -5 squared is 25. Okay, so our terminal arm is root 29. Okay, so root 29, there we go. Now we can write in some ratios. So we need all 3, so I guess we'll start with tangent. So tan theta was y over x. So tan theta equals -5/2. Sine theta is y over r. So sine theta equals -5/root 29. And we don't want to leave that root on the bottom. Let's rationalize this. So sine theta becomes -5/root 29/29. Cosine, same thing. So cos theta is x over r, which means cos theta is 2/root 29. So cos theta equals 2/root 29/29. Okay, it's rationalized. Things are good. They're in the place they need to be. Part B then asks you to determine the measure of theta to the nearest degree. So we need to find the angle that was in standard position. You can use your inverse trig ratios here, but you need to be careful about the signs. Okay, we are really looking for that original theta that was in that standard position. We've reflected it to get down into the bottom. Now up in the quadrant 1, all of the ratios need to be positive. So when you go to plug this in your calculator, make sure your ratio is actually positive. So let's do theta equals tangent -1, but in brackets, instead of putting -5/2, we're actually going to use +5/2. Okay, this will give us our angle in standard position. So grab your calculator, again, make sure it's degree mode, and we'll go second tangent 5 / 2, and you get 68 degrees. It says nearest whole degree in the question. Okay, so there's theta. So we're always going to use those absolute values, the positive version, when possible because we're looking for our standard position up in quadrant 1. Okay. Second one, a couple more. To the nearest degree, which values of theta satisfy this equation for the given domain? So they're telling us that my angle has to be in between 0 and 360. So it can't be bigger than 360 or it can't be negative. Okay, it's got to be in between there, which also tells you it will lie somewhere on your Cartesian plane. You're not going to spin around twice on there. You could only possibly go one full revolution to get back to 360. Okay, so there's my plane, and we can put the numbers on if you like: 0, 90, 180, and 270. Now, to the nearest degree, we need to find the values of theta which satisfy this equation. So cosine theta, I don't know the angle, but I know the ratio has to be negative. Now, our rule before gave us some insight as to which quadrants had which ratios being positive or negative. Now, quadrant 4 says cosine is positive. Quadrant 1 says all of the ratios are positive. So this terminal arm can't be in those two. Okay, it's actually got to be in the other two because sine is positive here only, tangent is positive in quadrant 3 only. So cosine could be in either one. So if I draw in a terminal arm here, the ratio for cosine says you actually have the x value and the length of that terminal arm. Okay, so I know x is going to be 3, and I know the terminal arm is going to be 4. Okay, the direction of those is important. So my terminal arm could either be in that second quadrant, or it could be in my third quadrant. Okay, and if you actually put some numbers on there, 4 is your terminal arm, and your shared side between those two triangles is your -3. Okay, the negative is going to tell you which direction to travel. So if I do -3 divided by my terminal arm of 4, that gives me a negative cosine ratio. Same thing underneath. Okay, the part that's different here, my y-coordinates are different. In my second quadrant, my y-coordinate's positive. Third quadrant, y-coordinates negative. That's what's going to give you the different signs for the sine ratio. Okay, but for cosine, they end up being both negative. Okay, so you could complete your triangle if you want to. Now, if you notice, we're going to have two different angles here that we need to find. Okay, one of those standard position angles in black. The other one we'll do in pink, that I could travel all the way around to get to my second terminal arm. So there are going to be two different angles here. Now, if I do this, I actually know the ratio for cosine already. Okay, I know what the values are. So let's just go straight up find the angle. Cos theta equals -3/4, which means theta is the inverse of cosine. Now we're again going to use the positive version of this to find that reference angle. Okay, 3/4. Okay, so that's going to give us the reference angle, and we can use it to work backwards to figure out the standard position angle, the other part that's missing. Okay, so that means theta is going to equal, let's put this in here, so second cosine, 3/4. My reference angle is 41 degrees. So we're just going to round it to the nearest whole number. And let's change the color into something that we haven't used style. Let's make it orange. Okay, so 41 is going to be our reference angle. And you can see it by taking these. Okay, so essentially what we just did was found, I don't want to use theta, sorry. Let's use phi. Okay, that angle in orange. We did the adjacent to it, the hypotenuse, that gave us the little tiny orange one, which is conveniently the same thing underneath. Okay, it's the same thing that happens twice. We just reflected it. Now we can use that little piece, that reference angle, to find the other two. So for the pink one, we had to go half the circle revolution and add a reference angle to it. So one of the possibilities for theta is going to be a half circle, 180 degrees, plus the reference angle of 41, which we found. So one of the answers for this is going to be 221 degrees. That is one standard position angle that creates a terminal arm for me that will give me this cosine ratio of negative 3/4. The other one, start with theta again. Now the other one doesn't go all the way around. It basically does the half circle of 180, but I can minus a reference angle to take me back out that little bit to get to that terminal arm. So we can do 180 degrees minus the 41 degrees this time. Now theta could also be 139 degrees. Okay, they're the two angles that will create those arms for me. Now we can check that on our calculator. So if I actually do cosine of my angle, I'm going to get this ratio, and the sign is important. So if I do cos 221, I get negative 0.75, just like our ratio says, and cosine 139, same thing. Now if I tried to do cosine of my reference angle, I'd actually get the same ratio, just positive. So it's showing me the other side, the other triangle. Okay, it's showing me the other little piece that I haven't accounted for. So everything works out here. I've got two answers. They both fall inside the domain. Both technically give me the same ratio. So be very careful. You do have to check both scenarios. Now, for a trig equation like the one underneath, they will give you a second piece of information to usually eliminate one of these choices. Okay, so here I had two quadrants which were possible. Underneath, you might have enough information to narrow it down to only one quadrant. If you can narrow it down to one quadrant, you've only got one angle. So this one is telling us tangent is positive, cosine is negative. So we need to figure out what quadrant that is first before we do anything else. So this is cosine, this is all of them, this is sine, this is t. So those letters will tell you which one is positive and where. So cosine is positive down here, but I need cosine to be negative. That gets crossed out. Quadrant 1 says all of them are positive, but cosine has to be negative, so that one's out as well. Quadrant 2 says sine is positive, which means that cosine is negative, so that seems okay, but that would also mean tangent is negative, so this one's out. Only one left. Tangent has to be positive here, which means cosine is negative. This is the quadrant I need to use. So let's draw in our terminal arm once again. It doesn't matter where it is, just draw it somewhere. So here it is. I can draw my triangle, and let's use phi for our reference angle. Actually, let's just use theta. Take that back. So in this quadrant, it's quadrant 3 because tangent is positive, cosine is negative. That's the one I need to use. In order to find the exact value of sine, I need to figure out how big the terminal arm is. I don't know that from tangent. All I'm given is the value of y and the value of x. Remember what the tangent ratio does. Takes the opposite of y, divides it by the adjacent. So my opposite is 3, my adjacent is 2√5. I can use that Pythagorean theorem to find that hypotenuse. Okay, so r is going to be square root x squared plus y squared. Fill in your information. So x squared turns out to be, let's do 2√5 squared plus 3 squared. 2√5, when you square it, you're going to get 4 times the square root of 25. Square root of 25 is 5, so 4 times 5, that'll give you 20. Plus 9. Our terminal arm is root 29. R equals root 29. There we go. Now that I know what r is, I know what y is also. I can go ahead and find sine. But here's where I need to be careful. For tangent theta, it says it's positive. But if I'm down in this quadrant, that actually means both coordinates are negative. Okay, I'm in a negative x direction. I'm also in a negative y direction. They've simplified and actually canceled them out. So tangent theta should actually be -3 over -2√5. The sign is important because when I go to do the sine ratio, Sine is going to be negative in this quadrant. Now, if I don't use a negative sign somewhere, that would actually tell me sine is positive, which means I'm in a totally different place. Okay, so for sine of theta, I need to do y over the terminal arm length. Y is -3. So sine theta is -3 over root 29. Rationalize, and you're done. Okay, so sine theta is going to be -3 root 29 over 29. This now says that sine is negative, which means it has to be in quadrant 3 exactly where we need it to. If I said sine was positive, it would be in a different quadrant, which wouldn't match with the information we were given. I didn't have to find the actual angle, just the exact value of this. Okay. Underneath, you've got your homework assignment, you've got your practice questions. I hope that helps. I've got a couple more videos for trigonometry, one more with the exact values. So we could have some special triangles that will always have the same side lengths, and that's what we'll talk about next time.